Oke, halo semuanya. Selamat pagi untuk teman-teman di Indonesia and good evening to those joining from the US. Welcome to Semiconductor Manufacturing 101, presented by PERMIAS Nasional and IEEE ITB Student Branch. We are super excited to have you all here today. My name is Raffi Ananta Alden, a third-year electrical engineering student at ITB and a staff member of the Circuits and System Society at IEEE ITB Student Branch. It's a real pleasure to be your moderator for this session. Moving on to our next agenda, we will have a greeting speech from the Vice President of PERMIAS Nasional, Frederick Gavin. Yeah, the time and screen is yours.
Okay, thank you so much, Alden. Good morning, people in Indonesia, and good evening, friends in the US, and greetings to everyone who's joining us today. I'm Frederick Gavin, as a Vice President 1 of PERMIAS National. On behalf of PERMIAS National, I'm honored to welcome you to Warekada event, Semiconductor Manufacturing 101. Today's event is a special collaboration between Indonesian institutions, ITB, and also PERMIAS National. And also we are collaborating with our speakers, Pa Stanley and also Pa Franklin. I would like to say thank you so much for all speakers, Pa Stanley and Pa Franklin, IEEE ITB, and also PERMIAS National and participants who made this event possible. And let's start this event and have this opportunity to connect and also expand our knowledge so we can explore more about semiconductor. Welcome and enjoy the webinar. I'll give back to Alden.
Okay, thank you, Gavin. Okay, so moving on. So semiconductors, we hear them all the time. They're the brains behind our smartphones, laptops, computers, cars, and basically all the cool tech that powers our modern world. So how are these incredibly complex, tiny things actually made? That's exactly what we're diving into today. We'll get an overview of the end-to-end process from the very beginning with silicon wafers all the way to packaging them up and getting them ready for use in our daily lives in the systems. So whether you're an engineering student like me, wondering about career path, or just curious about the technology you use every day, you are in the right place. And as what Gavin said, we're incredibly lucky to have two experts from the industry, both from NXP Semiconductors, to guide us through this. So first, please welcome Mr. Stanley Tutunang. He is a yield and process integration engineer at NXP. His work is crucial in the early stage of chip creation, ensuring everything integrates correctly and the number of working chips is high. So welcome, Mr. Stanley.
Halo semuanya, saya take over screen-nya ya. Let me share my screen. Okay, let me put it in slideshow mode. Okay, yeah. Good morning and good evening, everybody. So I'm gonna go over the basic semiconductor information. We know that we have conductor, we have insulator. Conductor simply is a material that conducts electricity, and we all know metallics are typically a good conductor: aluminum, copper, gold. Insulator, on the other hand, as we all know, doesn't conduct electricity. Material like rubber, plastic, wood, glass, right? So what is semiconductor then? Well, semiconductor sometimes conducts and sometimes doesn't conduct. As you can see on the periodic table on the right, we have silicon, right? We have germanium. These two are semiconductor material. There are also compound semiconductor like column 3 and column 5. They can also make semiconductor like gallium arsenide, Ga and As. There's also gallium nitride, gallium and nitride. They also make good semiconductor compounds. So again, we like it because it sometimes conduct electricity, sometimes it doesn't, and we can control when it conducts electricity and when it doesn't conduct electricity simply by controlling the voltage that we apply to the semiconductor material. So it's as simple as that. We can control when it's on and off. That's why we like it. So think of it as a switch, really. All our products that we use, they all use integrated circuits. Inside integrated circuits, there are tons of transistors. And transistors, simply think of them as just a switch. Can be on, can be off, and we can control it. There are a bunch of transistors, and we connect them together to make complex circuits. There are wiring that I'll show later that will connect those transistors, and because of all those wirings and the ability to control when the transistor can be on and off, we can make integrated circuit that does the things that we want for cell phones, for powertrain for a car, for airbag and stuff like that. So I want to show the big picture. All right. So in all our products that we use, our cell phones, our fridge, and stuff like that, if you open the inside, if you open the electronics, you'll see this PCB board. The PCB board has a bunch of packaged transistors that Frankie will go over later. But in order for this to happen, right, there are a bunch of processes that happen beforehand. So just want to show the big picture. It all starts with circuit design. So I'm sure I know the IEEE at ITB is definitely familiar with these. I actually don't have a background in electrical engineering, so I don't understand this. But I know this is circuit design, this integrated circuit. You have the transistors, you have the resistors, you have the capacitors. So it all starts with circuit design. What do we want to make? And the circuit design is basically like a circuit on paper, right? But it hasn't been manifested into a real chip product. So it all starts with circuit design. And then once you have the circuit design, we're gonna generate the reticle or the mask. It's basically the pattern that we're gonna print into the chip. Once we have those masks, then we're gonna actually make the chip. That's what we call wafer fabrication. We have the schematic, we have the circuit design, and we actually have to build it, and we call it fabrication. And this is where I work. I work in the wafer fabrication. Once you build the semiconductor chip in a wafer fabrication facility, you actually have to test them. So when you test them, they are still in wafer form. One wafer can have hundreds or thousands of chips, same chips. So takes probably 5 months to complete processing, but each wafer will have hundreds or even thousands of chip that you can use, that you can produce simultaneously. So after you test the wafer, the chips on the wafer, the ones that yield, meaning the ones that are successfully fabricated and they function, they will be singulated, and they will be cut one by one. So if a wafer has 1,000 chip, then there will be 1,000 of this. However, when you cut it, obviously it doesn't look like this. Franklin's team will have to put packaging on it, and then it's going to look like this. And then after the packaging is there, the chip will be tested one more time. It's called final test. After final test, it'll just go to customers, and the customers will put these chips in PCB board, depending on the application. So that's the big picture. So design, wafer fabrication, assembly, where we're going to put the packaging, we're going to test them, and it'll go to customers. This is where I work, and this is where Franklin works. Yeah, so that's the big picture. Hopefully that's clear. And this is just an even bigger picture. Not every company, not every semiconductor company does all three things. Not all of them does the design, the fabrication, and packaging and testing. For NXP, we do everything. We do the design, the fabrication, the testing, the packaging, and so on. Some companies only design, such as NVIDIA, Qualcomm, Apple. They design their own chips, but then they send their design to foundries, such as TSMC in Taiwan. Samsung also has a foundry service as well. So all they do is they just fabricate the chips, but they don't design. And then after that, it'll go to companies that specifically just test and package those chips. In order for all these to happen, to fabricate, there are a bunch of companies out there. I'm sure you've heard a lot of them. ASML, Applied Material, KLA, they are the big semiconductor equipment makers. So these companies here supply the equipment for the wafer fab facility, right? We also have companies that supply the raw material and the components for the testing and packaging, like all these, like Sumco, Zeiss, Integris, right? And for the design, actually, I almost forgot about this. There are softwares that these companies supply for the design process. So like Synopsys, Cadence, and ARM are the three top design software provider, right? So they provide these softwares to these companies and also to these companies down here. So, next slide. So here, I just want to elaborate a little bit more on the design piece. So this is a MOSFET transistor design symbol. Probably if you're an electrical engineering major, you're probably familiar with these symbols. This is a MOSFET transistor design symbol. But for me in the fab, this is actually less meaningful in the fabrication facility. This is actually what it's gonna look like for me. And then, so this will be fabricated into the wafer. So if you rotate this 90 degree, right? And then you see this right here. This here, the orange color is actually the wafer. When you start fabricating, this is what you see. This is just all orange. And then as you process the wafers more and more, you form this N plus. I'm not going to go into much detail, but this is a MOSFET transistor, basically. There are a bunch of processing that go into this. So this is what's happening in the fab, in the fabrication facility. It comes from design. That's what it looks like physically. And that's what we're doing here in the fab. And this is really, I just grabbed a slide from somewhere in the web. This is mostly for people who do circuit design. I don't really quite understand, but I know this is a NAND gate. NAND gate will have 4 different transistors. right? And this is the circuit diagram. However, for me in the wafer fabrication facility, this will need to be translated into the physical world. So this is what the circuit design looks like, trying to describe it more physically, what's actually happening. There are 4 different transistors. There are 1, 2, 3, and 4 transistors, and they need to be connected to each other. Same thing here. On this next slide, if you rotate it 90 degree, like I showed before, so these 4 transistors, 1, 2, 3, 4, they simply need to be connected. And all these connections between the transistors and the transistors themselves, that's what we're doing in the wafer fabrication facility. So to make long story short, all those transistors, they're really at the bottom. We call it the front end. They're the transistor module, but those transistors need to be connected to each other, and that's what we call it. What we call the back end of line module. If you on your phone, if you actually open it up, look at the chip, and you cut them, this is what you're gonna see inside. So the bottom part is the transistor module, the front end module, the MOSFET, and then the connections between those transistors, the metals, the vias, that's how we call it. They're gonna look like this. So a lot of the design, the circuit design. If I go back, since one reason for holding this event is to see how it's relevant to your career. These circuit design is mainly done by electrical engineers. The wafer fabrication piece is done by mostly engineering majors can do the wafer fabrication, so it doesn't have to be that specific. And Frankie will talk about the assembly later. Okay, so let me go back. So getting into more detail of the fabrication, I'm just gonna go through these real quickly, because I don't think we need to go into much detail. I just want to give a superficial description of what's happening in the fab. We have a bunch of processes that need to happen in order to make this. Some of them is called photo, etch, diffusion, implant, CMP, films, cleans. So I have 1 slide each. So we'll just go through that. Again, this is just a big picture from design to fabrication. This is what inside of a fabrication facility looks like. It's really clean, actually. It contains 1 particle typically per 1 cubic feet of air. So pretty clean, and they all use soot here because it has to be really clean. These connections between the transistors, they are actually really small. Human hair is 100 micron in diameter, but each of these lines are just probably 0.2 micron, so much smaller than the human hair. So any dirt can cut off these connections. So this is just an analogy down here. You have a floor plan of a house. In a fabrication facility, you simply build it physically from on paper into actual physical material. Maybe some of you heard photolithography. It is the goal of photolithography is simply to make patterns, right? If I go back to this, as you can see, some of these are metals, actually. Some of these have metals. The one in between don't have metals, right? We need to pattern the semiconductor chip. So in order to do that, we use something called photolithography. There's a mask. There's an opening here. There's an opening here. but there's no opening there. And then this is the wafer. You put photoresist, and then you illuminate through the mask. This gets the illumination. This area gets the illumination, and later through a develop process, this area gets removed, right? So photolithography simply is to make a pattern. It's as simple as that. And then we also have something called etch. Once you pattern it, right, you actually want to remove something from it. We use a process called etch. It uses a plasma. It's basically a gas that is electrically charged so that it can physically remove the material. Where to remove? We define it using the previous step here, which is the photolithography. So photo and etch, they go together. It's basically to make patterns on the chip. We have implant, as I mentioned before. We have the ability to control the transistor, whether it's on or off, by applying voltage to the transistor. And in order to define what voltage to apply, we implant atoms into the silicon in order to make the transistor to have the electrical properties that we desire. So it really is an ion source. There's a magnet that would just literally implant atoms physically into the wafer. We have films deposition. The most typical process is a chemical vapor deposition or physical vapor deposition. As you can see down here, we have these wirings, metals, vias. In between those wirings, we want to have insulation films. And in order to have that insulation, we need to deposit dielectric materials. Basically, it's basically like glass. Glass is a good insulator, so that these between these metals, there's not, so that they're not shorted, so that they are insulated. So we use chemical vapor deposition or physical vapor deposition. The gist of it is we have gases that we flow into the chamber, and the plasma will create some ions, and those ions will absorb into the surface of the wafer, and they will grow at the right temperature and pressure. So that's basically it. That's films and metals. We have diffusion. As I mentioned before, we can control the electrical properties of semiconductor. And in order to do that, we need to grow some layers on the semiconductor material. And one way to do it is by doing diffusion, such as growing silicon dioxide. The wafer itself is silicon, and you have oxygen coming in, it'll form silicon dioxide. So this is for diffusion process, and the temperature can be as high as 1,000 degrees C, actually. All those processes I mentioned before, they can be dirty, right? And in semiconductor fabrication, it is important that everything is clean. So we always have steps in between to do cleanups, to clean the debris from various processes. We use a bunch of chemicals, HF, which is to remove oxide. We have sulfuric acid, peroxide, ammonia, hydrochloric acid, and of course water to clean stuff up, right? So it's all built into the processing. As we deposit film, like I mentioned before, when we deposit film, those films will not be planar, right? Because we have something below it. CMP is chemical mechanical polishing. It is simply to make everything flat. It's just as simple as that. It's gonna mechanically push down on these humps, and we'll also use chemicals at the same time so that this humps will go away and it'll become flat, just like this picture down here. And then we can go on to the next processing. I think I can actually skip this one. And again, so all those processings at the end, the goal is to fabricate transistors, and those transistors can be connected to each other according to the design that the designer wants us to do. That's all I got, actually. Hopefully it all makes sense. Okay, let me stop sharing.
Wow. Wow, that's an incredibly intricate and complex process, Mr. Stanley. It's amazing how many steps are involved in just creating the patterns on the wafer. And yeah, so thank you for breaking that down for us. Well, maybe one quick question from my side before we move on. So maybe you could provide a brief answer. So as a yield and process integration engineer, what's one of the biggest challenge you face day to day in making sure this process works correctly?
For me, one of the biggest challenges for all these fabrication to happen, the tools need to work as intended. And many times the tools itself are very complicated and it does not work as intended. So many times the tool does not do what it's supposed to do. The equipment does not do what it's supposed to do. And because of that, the chip does not function. And then we have to figure out what happened. And that's the main challenge.
Okay. Oh, thank you for the answer. So yeah, we have to ensure what it meets our expectation like that. So
Right.
yeah, fascinating. So now we have these wafers covered in potentially millions or billions of transistors, but they're not quite ready for our gadgets yet. So this is where the next stage comes in. So we have our second speaker, Mr. Franklin Utama. We will have him soon. He's the package platform and systems manager at NXP Semiconductor. Mr. Franklin mainly deals with the critical steps after the chip is made on the wafer. So how it's protected, connected, and integrated into a larger system. So yeah, that's basically what Mr. Franklin does. So welcome, Mr. Franklin.
All right. Good morning. Good evening, guys.
Good morning.
Can you, I'm trying to share my screen. Can you guys see it?
Not yet.
Okay. How about now?
Almost. Yep, we can see.
Okay. You can hear me, right?
Yes, we can hear you clearly.
Yes, we can.
Okay, good. So, as Stanley shared earlier, so my name is Franklin Utama. We both work in NXP Semiconductor. I've been in the company for almost 27 years now. So I've always been in the packaging area. So tonight, this morning, hopefully I can share a little bit of semiconductor packaging to everybody here. So on today's agenda, I'm just going to share a little bit background as what Stanley had shown earlier on the semiconductor industry and semiconductor packaging overview on the high levels. So semiconductor industry, I guess, and I'll share some of the exciting why we are in this business. But just to give an overview of the map of the world where the semiconductor as often is referred to how we do the silicon, that's what Stanley just did an overview. and in vast majority, it's still very heavily in Asia, as you know. So Taiwan has the leading TSMC. This is divided by the 300 nanometer fabs and 200 nanometer fabs. Americas has about 18. This is data from the semi.org semiconductor. And Asia overall is about 79. Oops, sorry. Which breakdown. And China is coming up really fast. They have probably about 44 fabs now. Japan coming second. Sorry, the third after Taiwan, and then you get Southeast Asia and South Korea. Europe and I guess Middle East. This is like Global Foundries and a lot of other fabs that they have. This is maybe around 12 or so. So it is really it's a global industry. So and you see a lot of geopolitical activities going on right now, trying to kind of strategize where the fabs are. But it just kind of give an overview. Now this is Alexandra. Okay, so as a industry itself, I just want to give a flavor how big is in the semiconductor industry these days. So overall, around a few years back, we have as an industry about 600 billion US dollar in the scale, and the targeted revenue that this is a chart from McKinsey. By 2030, we are going to be about $1.3 trillion. It's a huge growth. The majority of the growth are in the industrial and auto. And I'll show you a few slides later about the auto industry. NXP is the place that I work is one of the number one leading suppliers for automotive. But you can see the growth that we see from 600 to billion to about 1.3 trillion. It's driven by generative AI. So this is a growth that, as you can see the chart here, from the wireless, and then this is the computing. The darker blue is automotive, and then about 140 billion, and then industrial, and you have consumer, wired, and then generative AI is not even showing in 2021, but you see the tremendous growth. As you see, what's the driving forces for this market growth? Back in 2000 to 2010, you have the growth on a lot of the analog. Then you see the laptop, the desktop, the mobile, the game consoles, home audio and video. And as you go to the next decade, we are in the era of smartphones, tablets, data center servers, and then now from 2020 and on, this is more on edge, where we call it edge, meaning is all intelligent system, and then now we have the AI. So it's very exciting. As I've been in this industry for 20 plus years, to see, what the potential growth and with the estimate, Deloitte is actually estimating with this kind of growth with 7.5% of compound annual growth rate by 2040 it could actually go about 2 trillion. So we'll see. There's a lot of challenges right now in the world as far as supply and the synergies, but I think we still should be on the track and this to be at least for the 1 trillion that we're targeting by 2030. This is only in next 5 years. Okay, so what's driving what I want to also go over some kind of types of semiconductors, as what Stanley shows earlier. There's the digital world and there's an analog world. So analog is continuous signals, and just a flip IOs, where you get the signal and the power, manage power in the electrical switches, battery management. And then the signal, this is measure signal and convert to data. So it's pretty simple, but you can also see the digital with the memory and then the logic, the DRAM, and then non-volatile memory that goes to a lot of the computers and stuff. And then the logics, you have the GPUs, as you see this big NVIDIA AI chips that goes to the board, and then the CPUs, also the programmable FPGAs and some of the ASICs. And all of this also goes to a mixed signal system on chip where you have everything analog, logic and memory that you kind of chip together to confirm a SoC, system on chips. Okay, I put a lot of the references. This is a lot of reference from the web that you can go look for as well, also in details. Okay, so why we have chips explosions that we see for the next 5 years or so. I'll take this from one of the pretty good graphics. So an average of a car these days, the newer cars, they have about 1,000 to 1,500 semiconductors that goes to the car. Electric cars, some estimate about 3,000 to 3,500. It's all the semiconductor that goes to it. They come from the safety. You get your airbag. This is kind of like a previous generation type that was still very important. That's very sophisticated, smart airbags. For the collision avoidance, if you get all your cars these days, you get everything that sensors that you can go from the front, the back, the side, parking assist, power lock, so on and on. Is very sophisticated, and it goes to a lot of semiconductors. NXP goes to a lot of the cars that we are one of the leading supplier, and powertrain, electrical, all the electrical engine connectivity, infotainment, and also some of the comfort. So it's exciting that we see. Right now these days, if I open my car, back in the day you can do a lot of stuff, but these days it's just a block. I mean, especially the electric car, you cannot really touch anything. It's all electronics. I also gave a little bit of flavor of this is one of the slides that we get from for iPhone 15. What kind of chips that goes with it, and then also the companies that goes to the phone. You get the memory board. NXP is actually plays in the what you call it, this NFC. This is for our NFC, and then also for the RF controllers, for the RF frequency board, and then the logics that goes to the Apple chips. Okay, so that's an overview of the semiconductors and what are the chips and what the projections. But now let's switch to the semiconductor packaging. As I use the same chart that Stanley has, this is a very good chart of the semiconductor value chains. A lot of the we call it OSAT. This is for outsourcing, assembly, and test. So the companies that the big one, ASC, Amcor, JSAT, Edge, I think this is a lot of the test companies. But I just also want to show some of the where are these in Southeast Asia. So Intel has a lot of has a factory assembly and test in Vietnam. Micron has this is all the Malaysian side, ASE, Global Foundries, UMC, Infineon. This is I think this is actually a Korean company. This is actually in Singapore. Texas Instrument has a fab in assembly and test also in the Philippines. Amcor, They have a lot in Korea, also in the Southeast Asia, but mostly in the Philippines. And then TFME, this is also all in Malaysia. Indonesia, we used to have one by PT Astra long time ago. I still remember I deal with them and went to assembly house in Batam, but then they get sold off to Unisem, I mean to ASAP and then Unisem, but I believe now they close. So there's opportunity there that I know the government of Indonesia is want to revisit and invest in assembly semiconductor, and hopefully that come to fruitions. Okay, so just a basic of why we do semiconductor packaging. As you see from what Stanley shows, what are, when we have the silicon that goes, and I'll have a slide later in the next slide on how that comes. But as far as packaging, the function is really when you have the silicon that Stanley shows earlier, the packaging function is to provide an electrical connectivity and also mechanical connectivity by the means of mechanical to provide the electrical connection from the silicon that we design that functions whatever function that is designed for, that goes to the PCB to the board. This is that goes to your final applications board. So the package itself, it helps for protections for the shield from the moistures, physical damage, and other environmental factors, and then also thermal management and also mechanical support, because all this generates heat. So as you know, when your electronics is getting too hot, then it will not function. So the packaging provide a really important functions to make sure that we have a really good thermal dissipations along with the thermal solution inside the PCB or the function or the device. This is a chart that I took one of our NXP FTF. This is like a technical form, so it's a public use. So Stanley went over the process earlier, where you get the silicon, the silica that goes to the silicon that where the device are grown and where they develop the silicon. Then it goes to a singulation where you can put it into the die, and it goes to the packaging, and then it goes as a chip. So just a high-level overview on the components of the assembly in typical. So it involves of a die cutting. This is where you have from your wafer, you have to be able to cut it and then make a singulation from a wafer. And then you attach it to a carrier. So if you see comes from the wafer back grinding, when you get the silicon, most of the time you have to thin it so you be able to get the package into the packaging. Do you do your what we call front end processes in our manufacture in the packaging, where you singulate it and then you put it into a die attach. So your die has to be put it into a carrier, either your lead frame or your substrate or a wafer level packaging. Then you have a attachment to those carrier, and then you cure, and then you do a plasma clean, and then this is a very important portion for the connectivity, where you get your silicon connected to the mechanical connection for the PCB that we call that either you through wire or you do a flip chip bonding, where you have like a small solder balls that you connect to the package the lead frames. I mean the carrier. And then after you do all the wire bonding or the flip chip side of things, then you protect it with a mold. Is an encapsulant, is basically uh, uh, a resin, plastic, or either ceramic, just to protect the outside. And then you do, after you have that, and then either if you have a lead, then you get a trim and form. If you have a ball grid where you have an array on the bottom, you do a solder belt attach, and then you do the back end portion where you make sure that you singulate it, and then you come and then you test and you get the final chips. So I'm not gonna go a lot more detail from there, but there's a lot of informations that available in the web also that you can go through. But in the nutshells, the process is you get a die cut, the wafer that you cut, that you have you attached to the carrier. You do your connectivity, and then you protect it to the with a mold, and then you single it, and then you ready for your test. Okay, I have two more slides. So just to show our semiconductor packaging evolutions, this is started in the 1970s, where you have what the so-called through hole. This is dual inline package, where you put into your board, you solder it down, and then you know, based on connectivity, and I have another slide on what you show that we show here, you goes to what we call a quad flat package. This is basically you coming from like maybe 8 or 16 I/O for the input output connectivity, and you goes to the 24, the 48, and it just continue as the device or the demand for the semiconductor become more complex. So it goes, you can see the leadless chip carrier, pin grid array, and then you have a ball grid array that goes to the hundreds of the IOs. And then you also have some of the issues with thermal. So there's this type of packages where you have a thermal on the heatsink that goes to the boards, and and then to the more complex now, you see the 3D integrated circuits that you see like in the NVIDIA AIs. So this is a good chart that I think is pretty informative. Coming from the 1970s, where you can see type of connectivity, what type of complexity that goes to all the way to the advanced packaging to the 2020s. Why, like I mentioned, we need those. It's I think as the demand of computing is getting really large, you go from like a single simple devices that we still use also, but it goes all the way to the increasing I/O and then increasing functionality, that you have a really sophisticated packages like the 3D integrated die stack or the wafer level 3D integration where you have a really complex devices, as the generation AI that we have seen. So that's all I have. So just want to hopefully this give you a flavor of the semiconductor packaging. So again, this is a very exciting industry. I'm very excited when I see this chart because it's keep reminding me, that the future is very bright in the semiconductor. So hopefully we can continue the growth and the trajectory. And I also hope that Indonesia will someday be a player, because we have the very rich resources. We have a very smart people like you guys here, very bright minds. I think it's just a matter of time that we tap it. I think we can do better than any of these countries. So I'm very excited about it. Thank you. Can you hear me still?
Yes.
Okay, good.
Okay. Okay. Wow, what a wonderful and insightful explanation. Thank you, Mr. Franklin. It's clear that packaging is much more than just putting a box around the chip. So yeah, it's very critical for performance, protection, and actually connecting it to the outside world, to the device that we are going to use later on. So moving on to our next agenda, we will have our joint Q&A session. So now we have some time to take some questions from our audience and maybe a few more general ones. So yeah, thank you again for Pak Stanley and Pak Franklin for those insightful explanation covering the journey from beginning to the end, from sand to system essentially. So, for our audience on YouTube, now it's the time to get your question in the chat if you haven't already. So, okay, by the way, we have our first question coming in. Let me read it. Maybe this is more for Mr. Stanley, I think. So it's from James Patrick. Which tools or TCAD do NXP use to fabricate the semiconductor devices? So maybe Mr. Stanley could answer this question. So
Yeah, actually, we use a lot of tools, and actually, those tools are produced by the companies in the slide that both Franklin and I showed. I think every semiconductor company, manufacturing company in the world uses tools from Applied Material, from KLA, from Lam Research. Yeah, it's pretty much, it's all the same suppliers. Yeah. So yeah. So remember that slide that has the name of the companies, the slide with the black background. Yeah. So Applied Material, KLA 10 Core, Lam. Yeah. So it's the same companies that everybody uses.
ASML.
ASML, obviously, that's for the patterning.
Yep.
all right, so yeah, basically there are lots of tools and it depends on their functions, I guess.
Yes.
So okay, moving on to our next questions. Maybe let me check for a bit. Okay, so we have our next question from Sam from UC Berkeley. So he said that, I'm curious, what kind of materials would you need to build an equipment that is used for the die cutting process? Well, I guess both of you can answer this.
This is for Franklin, actually, for sure.
So the die cutting, it has a lot of different way of cutting. You still have we use also a wafer saw with mechanical cutting. We do laser cutting with the lasers, and also there's also like a some kind of, well, it depends on the wafers, but that we have a stealth dicing where you use also some of the energies from lasers and combinations, but it varies.
Okay, thank you for the answer. So yeah, yeah, it varies on like what outcomes we expected of the
Yeah. So
wafer.
the wafer also, like it's different of the technologies as we go smaller and smaller the features. Also the miniaturizations of the die. So the die size when it get really small, there's a different techniques that we use. But the one that I guess very common now is just a wafer with the wafer saw. It's just a saw grind.
Okay. So yeah, thank you again for the answer, Mr. Franklin. So maybe because of our duration, we have a time for one more question. So we have our next question from Nicholas Alexander Susilo. So I'm pretty sure that both of you can answer this one. So what's the average yield for of NXP?
That is actually let me make sure. Yeah, that is actually a proprietary information. I'm not able to say what it is, but let me say it's close to the benchmark yield.
Okay, so yeah, maybe it's kind of a classified, yeah, but okay, so maybe I have a personal question from me. So for students interested in semiconductors, what kind of skills or subjects that are likely most important to focus on?
It let me maybe see my view on this one. It depends on the areas that one have an interest. So as Stanley shows, semiconductor, varies from the design of the design of the devices itself. That is a lot of the chip designers. Those are electrical engineerings, and like Alexa is on the design side of things, and Stanley is in the processes for the front end side, and he has a chemical engineering background, but um, he's very talented. He has all the other uh, uh, eh, uh, background too. He has other field that he has, but the major background is chemical engineering. I myself is in mechanical engineering. I have a degree in industrial engineering, but that is for packaging. We do a lot of mechanical engineers that we use, and also material science. As you can imagine, there's a lot of material development for the bill of materials, for the mold compound, for the glues. So that goes to a lot of the material science. We have a lot of material scientists. Then you can also have um, uh, variations between, I would say, the supply chains of things. This is a lot of the data analytics and all those type of engineering, also computer science, coding. So, but it's very high variations, but it depends on what field that one want to focus on.
Okay, so yeah, thank you for the answer, Mr. Franco. So maybe we have one more question, one last question before we wrap things up. It is from Alexandra. How do you think Indonesia can create more interest in semiconductor amongst high school students?
Mm, I don't know. I'll let Stanley answer this too from his point of view. But I think in the U.S., I think in high school there's a lot of STEM programs. So a lot of people at the high school, like from the high school levels that get exposed to this science technical programs, and then you have a lot of companies as um, like NXP or Intel or all those that I don't think we partner too much on the high school, but at least on the college side of things. But I think Indonesia can maybe benefit from exploring that and then kind of more exposure through like STEM programs. I don't know, Stanley, you want to add anything?
Yeah, I agree with Frankie. You know, in Indonesian, we say, kalau nggak kenal, nggak sayang gitu. So what we need is more exposure, I guess, to semiconductor. Because even here in the US, the exposure to semiconductor is not much, I would say, in high school. But like Frankie said, there are a lot of extracurricular activities that can potentially expose semiconductor to a lot more people. But I think, as far as I know, at least a long time ago, when I was in high school in Indonesia, I didn't see a lot of extracurricular activities. I did not know anything at all about semiconductor until I was in college, at the end of the college, actually. So yeah, so I think we need more exposure in order to generate interest.
All right, so yeah, what a great answers from both Mr. Franklin and Mr. Stanley. So yeah, well, unfortunately, that's all the time we have for the Q&A sessions. Well, doesn't feel like this hour flew by. So yeah, I think we all got a much clearer picture of the incredible complexity and precision involved in semiconductor manufacturing, right from the basic wafer process Mr. Stanley described to the essential packaging and system integration from Mr. Franklin, who walked us through. So yeah, a huge thank you to our speakers, Mr. Stanley Tukunang and Mr. Franklin Utama from NXP Semiconductors, for sharing your valuable time and expertise with us. It was incredibly insightful. Moreover, thank you also to PERMIAS Nasional and IEEE ITB Student Branch for organizing this event. And of course, thank you to everyone, to our audience for joining with us today, whether it's morning or evening for you. And of course, lastly, for the great questions. So we hope you found this session informative and maybe even inspiring. You guys can rewatch this session on the same YouTube link soon. So yeah, on behalf of the organizers, thank you all once again. Have a fantastic day. Have a fantastic rest of your day or good evening. Sampai jumpa.
Thank you.
Thank you.